So we want to start talking about the periodic table and really look into the periodic trends and have a better understanding of that. And so remember, Mendeleev organized the periodic table. He certainly wasn't the first, but he was most well known for his organization of the periodic table because things could be elements, for example, could be predicted that had not yet been discovered. Moseley, however, came along and rearranged everything so it was by atomic number once we were able to determine that number of protons. And that is the periodic table structure that we use today. There are periodic table groups that we need to know. So alkali metals are in group 1, and alkaline earth metals are in group 2. Again, alkali metals are very reactive. The oxygen group are also actually called the chalcogens. And then the halogens are group 17. Those are also super reactive, and our noble gases are then very unreactive. And so you'll notice that there are some things here in these notes about the A and B groups, although we more commonly use just the 1 through 18 numbering for our group numbers these days. The lanthanide and actinide series, again, are down below the periodic table. Majority of the periodic table are metals, and the nonmetals are then in the upper right. So there's a little review of a couple of things here. There are those anomalies like we talked about with copper and chromium, where they are minimizing the electron-electron repulsions by spreading out those electrons into, instead of two being in the 4s, having one promoted to fill that separate d orbital. Again, rare earth metals are filling the F orbitals, the transition metals are filling the D. And again, you know, we are going to talk more about these periodic trends here, but it's important to know that the trend is not really what we are going to focus on. We're going to focus on the why we observe that trend. How can we explain what we see? Okay, so let's talk a little bit about the arguments that we're going to use. It really comes down to 4 arguments. And the first one is effective nuclear charge, or Z, and then we use subscript EFF for effective. It's essentially equal to the group number. The idea is that the higher the effective nuclear charge, the more positive the nucleus and the more attractive force there is emanating from the nucleus that draws the electrons in or holds them in place. And so we're going to see this then relate to energy whenever possible. Again, that high effective nuclear charge is going to be really a strong attractive force of the nucleus is going to be greatest over on the right side of the periodic table. Upper right is our greatest force of attraction, and lower left is our weakest force of attraction. Next, we can think about distance. And so distance is going to really affect that attractive force also. So the attractive force is going to dissipate with increased distance. So distant electrons are loosely held and therefore easily removed. And again, we're going to use this and relate it to energy as much as possible. Shielding is another term that we're going to use. So the electrons in the core effectively shield the nucleus's attractive force for those valence electrons. So we're really only going to use this when we're going up and down a group. It does not affect things going across. The shielding stays the same across a period, but it is important as we go up and down a group. There's ineffective shielding within the same sublevel or energy level. Again, we're going to use shielding to relate to energy whenever possible. You know, they're saying here they think of it as like relating to dodgeball, okay? You know, you can stay behind the bigger kids to keep from getting hit. You're shielding yourself, okay? Electrons in the first or second energy level shield the outer electrons from the mother nucleus's attractive force. Again, you know, almost the same reason I maybe said last year that you want to sit in the back because you feel more shielded from, you know, the teacher's gaze, that, you know, you're going to be able to maybe get away with more stuff. And then the last thing we're going to use for our arguments is that we minimize those electron repulsions. And so this puts the atom at a lower energy state and makes it more stable. So again, we want to relate that to energy as much as possible. So those are our arguments. Now let's talk about the trends. So the first one we want to look at is atomic radius. And so remember, there's no sharp boundary between our atoms, but we're going to talk about radius as basically kind of half the bond length then for a diatomic molecule. That's how we would determine it. The radius for an atom is going to decrease as we move across a period. So from left to right, you can see there in period 2, when we go from lithium over to fluorine, that we are going to decrease in size. And it is going to increase as we move down a group or a family. Okay, so first of all, why do we see the trend that we see when we go across? Well, we see that we have a greater and greater effective nuclear charge as we go across a period. We're getting more and more protons there. And so because we're getting more and more protons, we're going to get a stronger and stronger force of attraction from the nucleus. So again, as we move across from left to right on the periodic table, there's that greater positive charge. Thus, the entire electron cloud is more strongly attracted and shrinks. This shrinks the electron cloud until the point where electron-electron repulsions actually would overcome that nuclear attraction and stops the contraction from happening of the nuclear cloud. So why are we seeing it go up as we go down a group? Well, as we go down a group, we're getting more and more layers of electrons, okay? That principal energy level, N, is determining the size of our atom. And as we add, again, those energy levels of electrons, it is increasing the distance between the nucleus and the outer electrons, making the radius of each atom much bigger. So as we go down a family, that attractive force also that is exerted by the nucleus decreases. And you can also then argue that our shielding is increasing. Those outer electrons feel less pull by the nucleus because they are shielded by those core electrons that are increasing as we go down. Again, it is not changing. Shielding isn't our argument as we go across the period. So we want to be careful with that. Okay, let's talk about ionization energy. First of all, let's define ionization energy. This is the energy required to remove an electron from an atom in the gas phase. And so it takes energy to rip that electron off of there. Removing each subsequent electron requires more energy. So we can have a second ionization energy and a third ionization energy, and that would be then removing the second electron or the third electron from the atom. And we'll look at those trends a little bit more, kind of what they are for specific atoms in a few minutes. Some of those subsequent ionization energies cost more energy than others. If we're ripping an electron off of something that has the same electron configuration as a noble gas, it's going to require a huge amount of energy. Okay. So you can see in our graph here, we get peaks in how much energy it takes with our noble gases. So those are things that are hard to remove electrons from, hence the reason that they don't react very easily. With ionization energy, our trend is that as we go down a family, that increased distance from the nucleus is actually increasing the shielding. And so therefore, it requires less energy to remove an electron as we go down a group. Again, our nucleus has a weaker force of attraction for those outer electrons as we go down a group and they get further and further away. So therefore, it's going to decrease that ionization energy as we go down. Across a period, it's going to increase, okay? And this is due to that increasing effective nuclear charge, that increasing pull or attractive force by our nucleus. And so it's going to require more and more energy to remove an electron as we go across the periodic table. Again, hence the reason that we see changes in the charge of our electrons or our atoms as we go across the periodic table. They tend to not lose electrons as we go across. They actually tend to gain. So we'll look at that in a second. Now, there are a few exceptions to consider here, and that is when we get to kind of the half-filled, filled sublevels, okay? Oxygen and nitrogen, for example. And so again, you'll notice here in the first bullet, so an anomaly occurs at messing up half-filled or filled sublevels. There's nothing magical about this, and the electrons are not happier as a result. The simple truth is that when electron pairing first occurs within an orbital, there's an increase in electron-electron repulsions, which makes it require less energy, or it's easier to remove an electron, and so therefore the ionization energy drops. Okay. But you'll notice here, never ever write about the fictitious stability of a half-filled shell, even though you may see it in the books. Like really, we're looking at minimizing electron-electron repulsions. So if we look at oxygen and nitrogen, it requires less energy to remove an electron from oxygen's valence, in spite of an increasing effective nuclear charge, and that's because of oxygen's P4 electrons. So as soon as we pair one of those electrons in oxygen, it ends up increasing the repulsion, and therefore it lowers the amount of energy needed to remove that electron from oxygen. Okay, and so you can see a little bit more in here also about that. Let's talk about electron affinity, though. Electron affinity is the affinity or liking that an atom has for electrons. And so basically it is that an atom will attract away electrons from other elements and add them onto itself. So this is how something becomes a negative electron. So if the addition of an electron is exothermic, then you'll see a negative sign on the energy change. Okay, think about how we talked about those energy changes in the last unit. So if it's exothermic, it'll be negative. The more negative the quantity, the more energy released, and therefore the more favorable it is. Okay. So things will want to gain those electrons if they have a lot of energy being given off when that occurs. We see that as we go down a family that it is going to decrease. This means it's becoming less negative, or for example, more positive and giving off less energy. Okay, it is less favorable as we go down a group to add an electron into an atom. And if we think about why, our nucleus is having less and less force of attraction pulling those electrons in, and we're getting a bigger and bigger kind of electron cloud there that we're trying to cram electrons into, that's actually increasing electron-electron repulsions, and when we don't have very much pull by the nucleus. As we go across a period, we're actually seeing an increase. This is why as we go from left to right across the periodic table, things tend to become negative ions. So again, by increasing, we mean that it's becoming more negative or giving off more energy. It's more favorable. Again, this is because we have a stronger force of attraction by our nucleus. The interactions of the electron-electron repulsions do kind of cause a problem here, but that stronger force of attraction really wins out here. Now, again, there are some exceptions here, and so you can see a few things here. The first lines on the diagram below connect adjacent elements. The absence of a line indicates missing elements whose atoms do not add an electron exothermically and thus do not form stable isolated anions. Okay, meaning there are things that don't tend to want to form these negative ions in there. And again, you can kind of see it. We're talking here in the area that's typically our positive ions. They just don't have a strong force of attraction. Okay, let's talk about atomic radii. So first of all, we use the term cation for positive ions. Okay, so sometimes students like to remember it because it's got a T in it, and that looks like a plus sign. Or they like to remember it that cats are positive. So they talk about cations being positive, like they have paws. Positive ions. When we lose electrons to become a positive ion, the atom turning into an ion is going to shrink. Okay, you've lost electrons. But when we form anions or a negative ion, those are actually going to get bigger. So we're adding electrons in there. First of all, we're adding something to the atom, and then there are more electrons which are going to repel each other, and that's going to cause that atom to get bigger. Let's talk about this word or this term isoelectronic. Isoelectronic is used to refer to atoms or ions that contain the same number of electrons. So it doesn't necessarily mean that they're the same number of protons, but it is, because then they'd be the same element, but it's the same electron structure. So like when oxygen forms an ion and when fluorine forms an ion, those both end up with a structure that's just like neon. So those are isoelectronic. And therefore, the number of protons is really going to affect their size more than really the number of electrons there. Electronegativity is another thing that we can think about, and this is the ability of an atom in a molecule, meaning like in a bond, to attract shared electrons to itself. Okay, so electronegativity is the atom's attraction for everyone else's electrons, whereas ionization energy is more like the attraction that I have as an atom for my own electrons. So the Pauling scale is used. It has a maximum number of 4, and you can see fluorine down, or francium, I should say, down here is at a 0.7, whereas fluorine is up here at a 0.4 in the upper right. So highest electronegativity up at fluorine. We do not include the noble gases in this because they don't have really attractions for other atoms' electrons because they don't form bonds. Why is fluorine the most? Well, it has the highest effective nuclear charge, the strongest force of attraction, and it's super small. Okay, so that also affects it. Why is francium so low? Well, it has a really weak force of attraction and it's really big. So that's going to cause it to not have a very big electronegativity. It just can't attract things very easily there. We can use this discussion quite a bit, thinking about bonding and things like that, and we will come back to that more. So you have 3 practice problems to take a look at. So I would like you guys to try those now, and then you guys can check. So pause the video now and go ahead and give them a shot.
Okay, so let's go ahead and check our work on these practice problems. The first ionization energy for phosphorus is 1,060 kilojoules per mole, and sulfur it is 1,005 kilojoules per mole. So what I'm thinking about here, first of all, are my electron configurations. Since ionization energy is going to be the energy related to removing one electron, I have to think about the electron configuration. So phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3, whereas sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. And so, again, if we kind of think about those orbital box diagrams here, for each of those, what's happening with the p orbitals. I would have 3 electrons that would be in the p orbital for phosphorus. They would each be in a separate orbital. And if I was thinking about sulfur, it would have 1 in each orbital. And then I'd have 1 paired up. And so that's really the key thing here. The fact that we have 1 of those paired up, well, that's going to be the first one that we'll take away. And so really, more electrons that are, together, paired up in the orbitals are going to cause more repulsion. So more electron-electron repulsion in sulfur means it will take less energy to remove an electron. Okay, it's like that electron is already repulsed by the one that it's with, and so it's easier to get it to move away, okay? To remove electron from sulfur. Okay, let's take a look at the next one. The next one has to do with ionization energies, and the first thing it asks you to do is just identify which element is which. So if we take a look at that, we see that our first element matches with neon, and our second element then would be sodium, and then finally we would have magnesium. And so we want to think about the largest first ionization energy. Well, the largest first ionization energy is always going to be from something that is a noble gas. Okay, so I'm going to think about it being a noble gas, and therefore the largest first ionization energy would be from neon. It would be hardest to remove an electron from that. Which one has the smallest and second ionization energy then? Okay, well, let's think about our elements. Again, we're talking about now removing 2 electrons. So the first one would have been a lot for neon. But to then take a second one away, okay, that wouldn't be nearly as much. And so, again, let's kind of think about what we've got here. 1s2, 2s2, 2p6. To take away that first ionization energy, that first electron, would put us to 1s2, 2s2, 2p5. And to take away a second one, it would put us down to 1s2, 2s2, 2p4. If we think about this for sodium, okay, so sodium has that, neon core, and then the 3s1. So to take away that first electron would put it down to neon, which we said is very stable. And then to take away one more, well, that's going to be putting it down to 1s2, 2s2, 2p5, okay? And then if we think about magnesium, magnesium starts with neon, 3s2. First ionization energy puts it down to just like sodium. And then take away one more, and it leaves it at neon, okay? And so again, if I'm thinking about those energy changes, which is going to have the smallest second ionization energy, this is really quite favorable. So this is going to be quite small to remove an electron and get it down to neon. But this is going to be really big. Let's see, we'll use this gray. This is going to be really big here for sodium, that second ionization energy, because it's removing it from a configuration that is like neon. We would also have a pretty small, a smaller change here, except for we'd have a pretty big force of attraction from the nucleus in this case. So the last one that we want to talk about is looking at ions. And when I look at these, first of all, I'm noticing here that each of these are elements that are in the same group. Okay, so I have beryllium, magnesium, calcium, and strontium, and really what I've got is very similar electron configuration. They're all ending in s2, so beryllium was 1s2, 2s2. We have magnesium is 1s2, 2s2, 2p6, 3s2. Calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then finally strontium, and I'm just going to abbreviate this one because it gets long with the D's in there, krypton, and then 5s2. So when I am making it a +2 ion, I'm really taking that last s orbital there, and that's what I'm getting rid of for each of these. Now, regardless of that, because of the fact that they're all in the same group, we're going to follow the same group trend, okay? And so as I'm going down that group, they are getting bigger as we go down. It doesn't matter that they're becoming ions, as long as they're all in the same group and they're becoming the same type of ion with the same charge. We're kind of taking off that outer layer, that valence shell of electrons, and they're still going to be getting bigger as we go down. And so we'll have strontium here as our largest, and we will have beryllium here as our smallest. And that's how we would rank those.